So the today lecture, as I mentioned, is the continuations of the previous lecture. Is about still we are about fusion reactions, but I just selected 3 sections for today. We have just few slides because some of the slides needed to go through the calculation and explanations. And as usual, I do the calculation and the mathematical here, and I will show you the results. So this is what we do every time. All right. Today we will talk about nuclear fusion rate, reaction rate. We'll talk about how many reactions will happen in 1 second. This is called nuclear reaction, fusion reaction rate. And then we talk about the distribution of the cross sections over the speed. If some particles have more are faster than the other ones, what's going to happen for the cross section? Remember, the cross section was the idea which come by the shooting the gun the targets, as you remember. And we talk about the gum of peak. So just 3 subjects, and then I will be free here if you have any question about those stuff. So what is the thermonuclear fusion reaction rate? So let me to talk about it a little more. So we are talking about the nuclear reactions. So we have some ionized gas. I mean the gases component are the nuclears, which these nuclears are different. Like you have a hydrogen and you have a two deuterium, for example. The deuterium are the same. So either you have a 2 same nuclear like a deuterium, or you have something different like hydrogen or helium or whatever light element, of course. Before the light element, which they are below the atomic number of the nickel, if you remember. If you have a 2 type of the nuclear, which first we consider the nuclear be different, A and B. And if the number density of each one is NR and NB, what is the NR? NR was the number per unit volume. If each one has the number density of NR and NB per cubic meter, then they are going to have a fusion reactions. For fusion reactions, for the rate of the fusion reaction, we quantify the nuclear reactions by introducing things which we call cross sections. So first we are thinking about the case that the nuclear A and B are colliding with each other with the constant relative speed. I mean, what is the relative speed? For example, if you are standing on the ground and the airplane is passing by you from the top, so you are standing and you don't move it, but the airplane is moving with velocity. So if you want to do any comparison between you and the airplane, you can talk about the relative velocity. The velocity of you with respect to airplane, but you are fixing, you don't move, so you can talk about the velocity of the airplane with respect to you. Yeah, this is called relative velocity. V, relative speed or velocity, whatever. If I talk velocity is the same as the speed, I just changed that word. So for thermonuclear fusion reactions, we think that there are 2 types of nuclear, A and B. Each one has a density, Na and Nb. And we suppose that they are colliding, or they are moving with the relative speed of the V. To be more precise, we can think about that one of the nuclear remains still is at the rest, and the other one is moving. So in your case, for example, we consider B is the heaviest one. For example, B can be the gold atom, and A can be helium. All right, the alpha particles. So alpha particle has the atomic mass of 4, and Au or gold is very heavy element. So in comparison to that, we can consider the gold atom as the one which is at rest. Now we send the alpha particles to this heavy atom. According to what we talked before, the distances which travel by the light atoms, by light nuclear, is given by the d. And if you remember, the d is the distance which is past traveled by the nuclear A. We can write the distance as the inverse of the NAB sigma. Sigma is the rate, the cross sections. So this is the distance which nuclear A will travel before interact with the nuclear B. Then, to calculate the thermonuclear fusion rate, what you needed is the time, the average time which taken for a fusion reaction to happen. The time which take for the fusion reaction to happen is given by the distances we travel by the nuclear A before the fusion, before the collision happen, over the speed. So speed we consider a constant, and the distance we calculated as a 1 over NAB sigma. So then you will get the expression for the average time. This is the average times of the happening of one fusion reactions. Then if you want to calculate the fusion rate is nothing, just the division, is just the ratio between the number density of the moving nuclear over the time which passed to the nuclear A to happen one nuclear reactions. So NA is NA, tau A you calculated, so just substitute here, you will get the quotient 3.40. This is the fusion rate of the fusion nuclear reactions between two elements, A and B. Okay, if somebody else do the opposite direction and the vice versa calculation, I mean, in this calculation, which we derive a quotient 3.14, we consider A moving and B is at rest. If you inverse the picture, if you think about A as a nuclear which is at rest and just shoot it B to the A, you will get the same equations. I mean, you will the RABA will be NAB over tau B, and surprisingly you will get NAB NA sigma V, and this is the same. So remember that the thermonuclear fusion rate between the gas with two nuclear A and B is independent from any assumption like who is moving with respect to the other ones. If you consider A moving and A is targeting to the B, or if you consider B is targeting to the A, so you get the same rate. It's like a laser. In the laser also we have something like that. In the laser, laser is based of the transmissions of the light elements from the layer to the layer, basically, if you want to tell. And here also the enchantment rate or the rate of these transitions given by RAB or ABA there will be the same. Any question? Okay, what happens if element A and B are the same? If element A and element B are the same, the situation will be different. Remember that sometimes A by A cannot make any fusion reactions. I mean, the first two elements should be different in many cases. So if there are different type of the nuclear like A and B, and if the number density of one of these is NA and one of the other one is NAB, so the number of different combinations of the A and B, which they could be provide a list for your reaction, is just NA times NAB. But if all the nuclear had the same component, same particle types, then it is clear that a given particle cannot react with itself. I mean, A1 cannot react with A1, but it can only react it with the other particles, which they are same, but they are not sitting at the same place as the first nuclear. Yeah, it's like you have 10 electrons. I mean, the electron number 1 make interactions, the Coulomb interaction, with all other electrons except itself. Yeah, that's very clear. So the first things we need to know is that how we calculate the previous term NA, NAB in the equation 1314. You can guess that is A and B are same. It could be NA square. Yes, you can guess that if NA and NAB is the same. I mean, if the nuclear fusion happen in the neutronous gas with the same nucleus A. But it's a little different because you can use the combinations, the mathematics. You have an N partner, and they wanted to make an interaction with each other, except the interaction with itself. So it goes to the combination problems. The number of the pairs which you make a possible reactions for you is not NA. I mean NA square. It will be half of them. Do you know why the half will appear here? Have any idea why this factor 2 appear here? Remember the example I told you about the electrons. If you have 10 electrons, so you can tell me that how many independent interaction will happen between the electrons. Can you tell me if you have 10 electrons? How many possible interactions will be the number of possible interactions? Are you here? If you have 2 electrons, for example, how many interactions will happen between them? 2 electrons. Electron 1 make a repulsive force. The electron 2 and electron 2 repulsive to electron 1, but their repulsive force or the Coulomb force between them is the same. So just one time happen. If you have a 3, how many happen? How many interactions between 2 electrons? If you have a 3 electron, how many interactions will happen between them? The number will be 3 times 2 over 2, so 3 times. So electron 1 will make interaction with electron 2, and it will make interaction with electron 3. That's all. Then you go to the electron 2. Electron 2 make interaction only to electron 3. And what about electron 3? Does it make any interactions to the electron 1 and electron 2? No. So we get 3. Are you there? Yes. Okay. So if you have 4 electrons, tell me how many interactions will happen. If you have 4 electrons, electron 1 make 3 interaction. 4. Listen to me. You have 4 electrons. Electron 1 make interaction to 2 and 3 and 4. So 3 you have here. Electron 2 make interaction only to 3 and 4. Cannot make interaction to the electron 1 because already did one time. Interaction of 1 and 2 is the same as interaction 2 and 1. 3 may make only to 4, and 4 do nothing with the others. So you have 3 plus 2 plus 1 will be 6. 4, well, the number is 4. and whatever. So now you understand what I show you in the slide. If you have n nuclear, so the number of interaction will be n times n-1/2. And there is one thing here. The number of nuclear is a big number, it's a large number. So there is no difference between Na and Na-1. I mean, the Na, n is almost same as the n. For example, n is Avogadro number. So if n is 10 power 23, then n-1 is almost n. Is almost n, only for large n. N, instead of the n minus n-1, you can write as n, so n squared. So instead of the factor here Na and B, you have just Na squared, half. Okay. Let's go to the, do you have any question about here? Okay, we talk about the speed of the particles. We say that we are considering that a type of the ionized gas with two types of nuclear A and B, and we consider V as a relative speed between A and B. But you have to think that the particle or number of particles is very large, and each particle has a different velocity. So what you can do is that what you will do is that you have a distribution of the particles over the velocity or speed. So the cross sections should be averaged over the speed. So we arrive at a concept which is called a speed average. Let us suppose that if you have a nuclear and the relative velocity of them is v, so you always can tell me that how many of the particle has the velocity between v to v plus delta v. This number which you can count is the probability of a pair reacting nuclear, and it's given by p, pa, as a function of v dv. The subscript r show that the relative speed. So the average value of fusion cross sections multiplied by the relative speed is this. You see that this is exactly the same as the mean free path. You remember mean free path of the particle we calculated before? It was the average distances with the particle travel before they reach before they make a collision with the second particles. That we call it mean free path of particle. Here you have an averaged over the speed. So the average of the number of the particle with the speed of the v, which can make the reactions, fusion reactions, is given by the expression 3.16. And you can calculate this integral if you have a distribution of the speeds. It is important to show you that the fusion rate which we calculated in the last two slides is actually dependent to the integral 3.16. I mean, instead of the sigma v, which we write in the previous examples, I mean, here we have a sigma v, and here we have a sigma v, also sigma v, sigma cross section times v. We have a distribution of velocities, so you cannot talk about spatial velocity. You have to talk about the average of this. So average of the quantity sigma v here should be replaced, and it is the correct expression for the fusion reaction rate. Equation 3.17 and 3.18. But to calculate that, you need the probability of the distribution of the nuclear pair versus the velocity. I mean, you have to know that how many of the nuclears have a spatial speed between 2 v and v plus delta v. So if you back to the derivations of the fusion rate, which we calculated before, you see that instead of the sigma v, you always have to substitute the average of the sigma v. And to calculate the average of sigma v, you need the probability distribution of the nuclear over the speed. So if you back, for example, if you consider the time which the average time of traveling of the nuclear A to be targeted to the nuclear B. So the design this time is not 1 over NB sigma B. It should be corrected as equation 3.19. Should be corrected as 1 over NB average of sigma B. And then if you back to the previous example, previous equations, equation 3.17, substituting the average of sigma VR in the equation 3.17 gives you the correct expressions for the RAB. And you similar way, if the particle, if the nuclear are the same, like deuteron, for example, then A is equal to B, and you remember it was appearing a factor of 2 here in the equation 3.21. But the other things are the same. So instead of sigma V, just substitute the average of the sigma V over the distribution of the speeds. What is the distribution of the nuclear over the speed? So for many situations, we are lucky that in many situations in astrophysics, the speed distribution for the particle is the Maxwell-Boltzmann speed distributions. Anybody remember about Maxwell-Boltzmann distribution in the chapter 20 of the Halliday-Reznik? What is this Maxwell-Boltzmann distribution? What does it mean? Equation 3.22. What does it mean, these equations? T is the temperature, K is Boltzmann, constant is a number fixed, M is the mass of the particles, M is the mass of the particle, and the V is the speed of the particles. So can you tell me that what is the meaning of the equation 3.22? Equation 3.22 gives you the number of the particles which have a speed between V to delta V. Okay? So because you have finally some number, total number for the particle, you can expect it that the integral of these expressions over the whole speed will be 1. That's we can show actually here by the Mathematica. I will show you that by Mathematica why this integral should be 1. So we have a P here. So this is our P. So P is, what is the P? P is M over 2 pi KT power 3 over 2 times exponential minus M minus mv square. I deleted the VR. I write V, okay? Over 2kt. 2kt. Okay. Times times 4 pi V square. V square. Okay. This is the distributions. This is your distributions. I can plot these distributions if you want. We can plot this distribution. I mean, you can substitute. First, I want to show you the integral of these expressions. This expression is 1. So to show that the integral of this expression is 1, you can go through this and find the integral. So we replace the expression here. So this is dV. What is the minimum? The minimum speed, we consider 0 as the minimum speed. And what is the maximum speed of the particles? It could be any numbers. I mean, it can rise up to the, theoretically, it can rise up to the infinity, but basically, the maximum speed is c. If you take the integrals, it will give you a constant. We have to wait for the running. So this will be 1, as I told you. So this is actually the probability, okay? This is actually the probability of finding the particles with the v speed of v up to v plus delta v. So now I wanted to do one thing. I want to plot this function. So to plot, let me to do one thing. I want to substitute m by kt, for example, just for fixed time. I want to plot this function for fixed time, so it will be like that. So then I want to plot this function to see. I want just to show you what is the Maxwell-Boltzmann distributions. So this is the Maxwell-Boltzmann distributions, and the speed, the range of the speed of the particle is from 0 to infinity. So then, wait me. Okay, infinity can't do that. Okay, 0 to 10. This is the Maxwell distributions, as you see. There is a peak here, yes? This peak, what is the meaning of this peak here in the Maxwell-Boltzmann distribution? Do you know? Anybody know what is the meaning of the peak? What is the meaning of the peak? In Maxwell-Boltzmann graph. Maximum probability. It is maximum, it is the maximum speed, which they can reach it. This is the maximum. It's happened here, and this is the maximum probability. Exactly. Do you know how to find this? How I can know that? You can use a get coordinate here, and you can go there and you can find the get coordinate. The coordinate for maximum is 1.4 as a speed, and the maximum is 0.58. Okay. Theoretically, you can do one more things. You can find the maximum by that. Just write maximum his functions over v. I think it will work. Maximize. So this will be the maximum value of that. Okay. And you can simplify this. I mean, this number, I want to show you what's the number. This number will be 0.58, as I mentioned to you. Either by the graph reading from the diagram, or either by taking the maximum minimum, you can find the maximum probability and maximum speed of the particles in these Maxwell-Boltzmann distributions. All right. Let's go to there. So you have a Maxwell-Boltzmann distribution, so you can substitute here and making the integrals. So if you substitute here, you will receive the v square was for Maxwell. You have one more sigma here, so you have to think about the integral and make this integral more simplified. To calculate the integral, we can convert the integral. So firstly, you can do the integral very clearly. I mean, you have the p now, yes? So you have now the p, so I want to just to go and calculate average of sigma v. So what I have to do is that I have to take the integral of this sigma v. So I mean, here I have to write one other v. Sigma, this is the sigma v. Let's see what's going on here. You can calculate it, and this is gives you actually the average of sigma v. So you have the average of sigma v. You can simplify these expressions also. I mean, everything you can do by computer, but even I did all by hand when I was a student, so I did it all by hand. So the things which happen is that the average of sigma v will be proportional to the radical t, as you see, root t. It will be proportional to sigma root t. Other technique is that you change the variable from v to energy. So if you know that the particle has just kinetic energy is mv square over 2. So instead of the velocity, you write rooted to e over m. Then dav will be changed to de, as you know. Should I repeat it that because you know this is from calculus. This integral can be written in the terms of the integral over E. And you will get the same results. You will get the same results. All right. And if you substitute that, then you will get the expression for the fusion rate. There is one problem here. The problem is that this sigma, which we write here, somehow the sigma is not constant. This is the problem. If sigma be constant, you can use the what I calculated by Mathematica here. This is for constancy. But if sigma is a function of velocity, you cannot do anything. Yeah, so it will get you get into trouble, for example. In this case, you can generally speaking in nuclear physics, sigma is not constant. So unfortunately, so sigma is a function of E, so your integral remain as you see. So you need still information about sigma. But you know that the cross-section, fusion cross-section, you had that, yeah? Previous lectures, you had the fusion cross-sections. It was, you know, it was given by the Gamow expressions. Yes. It was given by SAE, remember? Over E exponential minus EG over E root. So we have the model for the cross-section, fusion cross-sections, sigma, over the range of energy by study the tunneling effects, you remember? So if you substitute that, you will end finally to the equation 3.223. This equation is very complicated because still you have the factor SAE, but as we mentioned before, SAE is a special function which almost is the constant. So if SAE is a constant, we can calculate the integral easily. I will do that for you. Just I want to show you that there is nothing here which cannot be calculated by computer. So let me to write. So I consider S as a constant. So S as a constant. So exponentially, exponentially what? Exponentially minus. Can I write energy? I write energy X, okay? Because E is a little is supported by the and EG over X over. I just writing the calculation, the expressions here, and energy over integral over E. So X here is energy. So I can mention here that the X means energy, and the EG means the Gamow energy. Okay, energy. Let's see how goes the integral. So if you click it that, it is possible to calculate the integral, but I think the integral will be very complicated. It's given expressions. You see the expression is very complicated. It is given like a function of major G. So major G is not a simple function. It is a very complicated function. It is very complicated functions. And but anyway, I mean, if S is constant, you can calculate the integral, as you see. But as I told you, S is not very constant. It is very close to be the constant. So let's go and study this integral. Integral SAE multiplied with Gamow factors. The technique is that this exponential is like exponential x plus y. So this is like exponential of x plus y. So you can write this like exponential x times exponential y, and then you know what is happening is that the Gamow distributions has a peak. Remember, this is the Gamow. This is a Gamow distribution. It has a peak. I want to tell you that all the energies do not have any contribution to integral. Only the energy at the peak will be important here. So I mean, there is only one energy which is make a contribution to the integrals, and this is the Gamow energy, and this is called Gamow peak. This peak of the energy. So by this technique, if you find there is a gamma of peaks, so the gamma of peak is given by Eg times root kt square. So this is, you can find it. Do you know how you can find this? The technique to find the gamma of peak energy is that you have these functions. Where is our functions? That was our functions, huh? This is our functions. So I can maximize these functions again, maximize this versus what? Versus x. Let's to see what's going. So for different ranges, we'll get different factors, but the maximums comes like solutions for these equations. You can calculate. I mean, basically you can calculate that. So you just copy this here. It means that you have to solve this equation and times to -1. It gives you the this is x. So I have to write here this. So you say this is the peak. Which one is the peak? The root which gives you the positive energy is the peak. So Eg kt over 2 is the peak energy. So okay, you can get the expressions here. This is the maximum. You can find it from here. All right, that was my presentation for today. So I don't want to make the lecture longer. So you see that you get some information about the nuclear fusion, nuclear reactions rate, calculating of that, and we borrow some informations from the previous lectures when we talk about the nuclear fusion cross sections versus the energy, and you see that in the calculating the fusion real rate, you need to consider the fact that the particles have a different speeds, and they have a distribution of the speed, and you cannot talk about the one speed of the particles, so there are different speeds. And we use the Maxwell-Boltzmann distribution for the speed as a good approximation for many astrophysical applications. And then you remember that to calculate the sigma v, we cannot take the sigma as a constant. So the trick was that you write the integral in terms of the energy, and then you consider the information which we had before studied about the cross-section in the fusion reaction versus the energy. And then we show that the important comes from the peak. Of course, you can calculate the integral exactly as I mentioned in terms of the measure functions, as you hear, but there is very complicated. So the best way is this is the exact expressions. This is the exact expressions. You can conditional expressions. You can use these conditional expressions. But the best technique was that you know that the cross section versus energy is important only around the spatial energy, and this is the peak energy. So, and that's all. So if you have any question, ask me. Otherwise, we finish.
All right, Daddy. Daddy, look at the floor.
What's that?
It's
okay.
A thread. It's a thread to my room.
Okay. Do you have any questions?
Are you talking to me?
Yeah, I know I'm talking to Steve.
Yes, I have a question. This is a thread that goes to my room.
To what?
A thread that on the floor, you see? See
Okay.
on the floor? Look at the floor. Look at the floor. This is the thread.
Okay.
That's the thread.
So I will up the lecture slide now here. As usual, you can go there and read it. The video of the lecture will be exactly the same, as you know. So I have to make a new folder here, Skeleton homework, and I will share this link to you. So the homework will be here. So I will send the homeworks. So the first homework will goes to the to the lecture of homeworks. But actually, there is a risk that if you uploaded I will stop the recording.